Hi everyone, welcome to this series on probability for business analytics. My name is Teja, and in this video, we're going to look at the notion of independence. So independence, just like conditional probability, is a very interesting uh, rule that you should be aware of. So two events are independent. Two events, let's say A and B, are independent if the probability of A intersection B is equal to probability of A times probability of B. Okay, so this is just a definition of two events being independent. So when would this happen? So let's again draw this sample space, and let's say there's an event A and there is another event B. Okay, this is event A, this is event B, and there are other parts of the sample space, some other outcomes which we haven't categorized as part of any interesting event. So let's say A and B are these, and this is their intersection. Okay, so there's a belief that we ascribe to the outcomes there. So probability of A intersection B would be some probability mass that we have assigned over here. We also have probability mass assigned to A, event A itself, and we have also probability mass assigned to B itself. So the product of these two, if it is equal to this intersection, then the two events are called independent. Okay, so what does it mean actually? What does it mean in terms of interpretation? It just means that, so this is equivalent to saying that since we remember from the definition of conditional probability that this was just equal to probability of A times probability of B given A, right? Or we can also write probability of B times probability of A, probability of A given B, right? So let's pick this version. Then we can see that from this and this, we can see that probability of um, B given A is nothing but probability of B itself, which means that knowing that A has happened has no bearing on my belief or B. So even if I tell you that A has happened, something in A has happened, one of the outcomes or elements in A has happened, then it doesn't tell me and it doesn't let me update the belief over B. That means that A and B have kind of no information gain if I know one or the other. Okay, so that's what is meant by independence, and it's kind of crucial, as I was just alluding to in the last video. The whole independence is the bedrock for the whole field of graphical models, and if you kind of understand independence, then you can really appreciate models that I discussed in the last video, as well as models such as latent delay allocation, which is used for topic modeling, or even naive-Bayes classifier. And that brings me to the next point. Okay, so a disclaimer: the models that I'm mentioning, like naive-Bayes classifier, latent digital allocation, or things that I mentioned in the last video, like hidden Markov models, um, they all need the notion of a random variable, which I have not yet introduced, but I will discuss it in a subsequent video. But for now, since I mentioned naive Bayes, I'm going to talk about a related concept similar to how conditional probability is related to probability. There's also conditional independence. Okay. So what does conditional independence mean? It's basically the same as independence, but once you condition on a third event C. So maybe so let me draw this weird looking event here with the dashed diagram here. Let's say that's event C. So you can see that probability of maybe in this version, probability of A intersection B given C. Okay, so conditional independence means this property is true. Probability of A intersection B given C is probability of A given C times probability of B given C. Okay, so I drew an event there, which is C, which has some overlap with A and B, and it also has some outcomes which are outside, right? Now you can see that the intersection region is still the same. So probability of A intersection B given C is here, and given C, um, there must be an updated belief on these outcomes in the set A intersection B. If that belief is equal to my updated beliefs on the probability of A given C and probability of B given C, then A and B are conditionally independent given C. Okay, so it could be. So here's a disclaimer, and we'll not go into this in detail, uh, but it's definitely interesting to check out once you are familiar, once you are comfortable with the notion of independence, conditional independence, and conditional probability. That so here are the disclaimers. So sometimes events are independent, but conditioned on maybe another event, another event. They are not. Okay, sometimes they are independent, but on conditioning they become dependent. Okay, and sometimes they are the opposite. Okay, and also sometimes events are um, pairwise independent, but not fully independent. Okay, so what do I mean by this? I just introduced a new notion called pairwise independence, but so let me explain that. So let's say I have three events, A1, A2, and A3. So maybe, so these events are independent of each other if probability of A1 intersection A2 intersection A3 is the probability of A1 times probability of A2 times probability of A3. Okay, now if these events are pairwise independent, then we know that probability of A1 intersection A2 is equal to probability of A1 times probability of A2, and probability of A2 intersection A3 is the probability of A2 times probability of A3. Okay, and probability of A1 intersection A3 is probability of A1 times probability of A3. Okay, uh, so it turns out that uh, if this is true, it may not imply that this is true, and vice versa. So this is what I just wanted to say, that you just need to be a little bit careful about pairwise independence and independence in general.